This past week, on June 8th, was World Ocean Day. A day to remember how the ocean has given life to us all. To honor this Day of the Seas, let's take a look at what algae looked like 65 million years ago. To do this, let us return to AlgaPark and take a tour of their facilities.
Welcome to AlgaPark, where algae always rules the world.
AlgaPark has collected many specimens of phytoplankton over the years. One of the really special ones is called coccolithophores, which date from the late Triassic. Coccolithophores were extremely abundant during the Mesozoic Era, also known as the time of the dinosaurs, reaching their apex during the late Cretaceous. However, there was a sharp drop during the Cretaceous Paleogene extinction event, when more than 90% of coccolithophore species became nearly extinct, and today only make up 1 to 10% of the ocean's phytoplankton. Each coccolithophore enclosed itself in a protective shell of coccoliths, calcified scales which make up its exoskeleton, or coccosphere. The coccoliths were created inside the coccolithophore cell, and while some species maintain a single layer throughout their life, only producing new coccoliths as the cell grows, others continually produce and shed coccoliths. The primary constituent of coccoliths is calcium carbonate, or chalk. Calcium carbonate is transparent, so the organism's photosynthetic activity is not compromised by encapsulation in a coccosphere. While the exact function of the coccosphere is unclear, many potential functions have been proposed. Most obviously, coccoliths may protect the phytoplankton from predators. It also appears that it helps them to create a more stable pH. During photosynthesis, carbon dioxide is removed from the water, making it more basic. Also, calcification removes carbon dioxide, but the chemistry behind it leads to the opposite pH reaction. It makes the water more acidic. Coccoliths are the main component of the chalk, a late Cretaceous rock formation that outcrops widely in southern England and forms the White Cliffs of Dover. The area is situated along the undulating shoreline between the towns of Exmouth in East Devon and Studland in West Dorset, and is known as the Jurassic Coast. This Jurassic Coast is renowned for the nearly continuous 185 million year record of Earth's history exposed in its sensational sea cliffs. It shows the rapid diversification of life, as well as several major extinctions, over the period of the Mesozoic Era. So, the next time you see the cliffs of Dover, you aren't just looking at the beauty of nature, but also a time machine back to the time of the dinosaurs. Next on our tour of AlgaPark is our genetics department. Here we are unlocking the mysteries of algae and leading the future of phycology. In particular, CRISPR/Cas9 has revolutionized genome editing fields with its simplicity, efficiency, and accuracy compared to previous nucleuses. CRISPR/Cas9 induced genome editing is being used in numerous organisms including microalgae. Microalgae have been subjected to extensive genetic and biological engineering due to their great potential as sustainable biofuel and chemical feedstocks. Historically, the green alga Chlamydomonas reinhardt has been the focus of most molecular and genetic phycological research. Even outside of AlgaPark, industrial genetics is being used, as we can see in an article from February 22, 2021, titled, "Green Algae Reveal 1 mRNA Encodes Many Proteins." Gene expression in eukaryotes was long held to be monochistronic, that is, a single gene makes messenger RNA, which encodes a single protein. Recently, a team of researchers has found numerous examples of polycistronic expression, in which 2 or more genes are encoded on a single molecule of mRNA. They found this in 2 species of green algae, Chlamydomonas reinhardt and Chromachloris ophingiensis. Overall, approximately 20 different microalgal species including cyanobacteria have been successfully genetically modified to date. With genetic engineering, scientists can develop algae that grow faster and ward off deadly bacteria. They can create algae that produce more oil, which can then be turned into biofuels or biodegradable plastics. Or, they can engineer algae to be more nutritious, whether for livestock or people. Even though genetic engineering has been around since early human agriculture and has helped us create cows, dogs, and the wheat we eat today, some people still question the morality of genetic engineering, and in accordance with the guidelines of the AlgaPark tour, the next part of the tour is presented by our in-house philosopher and mathematician, Dr. Ian Malcolm. Take it away, Dr. Malcolm.
Thank you very much. You have seen a lot on this tour of AlgaPark. You can see the amazing connection between humans and algae. Yet we have to question ourselves, are we playing God when we are using genetic engineering? Humans using genetic technology to unlock the mysteries of life. It's like a kid who found his father's loaded gun. We don't know the effects humans can have on this planet. We can already see this with climate change. But unless we stop existing, humans will always have an effect on Mother Earth. It is up to us to choose whether that effect is for the good or detriment of this planet. We need to preserve the waters which have given us life. It is because of these waters that life found a way.
Thank you for visiting AlgaPark, and we hope to see you again on another tour. And like Dr. Malcolm says, it is because of the ocean that life found a way.